Good evening, class. I'm Mohit, and in today's class, which is the first class of this quantum Hall effect offered by NPTEL, this is of the semester August semester 2025. So, I'll be talking about the quantum Hall effect and the chapters which we'll be covering in this coursework. Then I will go on talking about the basic preliminary request for this course, and I'll solve few of the problems and we'll talk about how this quantum hole is different from the classical hole and why it is important to study these kind of effects phenomena in the condensed. So having said that, I'll start with my introduction and this course introduction. So this course name is Quantum Hall Effect, as I said. And now coming on to the instructor. So instructor is Professor Saurabh Basu. He is from IIT Guwahati, and I am the TA for this course. My name is Mohit, and I am a PMRF scholar at ISC Bengaluru, the Department of Physics. So if you have any question, doubt, or suggestion, you can drop me a mail at mohitjar@isc.ac.in. I'll be happy to reply your queries. Yeah. Having said that, now let's move on to about this course, what the course is all about, and what we'll be covering in this basically the coursework. So we just see this thing. Yeah. So welcome to the quantum Hall transport and Hall effects. Hall transport and Hall effects. So in this course, you will explore how electrical transport behaves in the mesoscopic systems. So let me just briefly write it, whatever I'm saying. Electronic transport in mesoscopic system. This includes the conductance quantizations. Yeah. This will uncover both classical, will be uncovering both classical and quantum effects. I'll start with the classical one and then we'll go on to the quantum effects where the classical mechanics fails to explain the phenomenon. And definitely I'll start with the historic background. What is the classical Hall effect? How it was discovered, by whom it was discovered, and then how the journey went from the classical Hall effect to this quantum regime. So then in this coursework, I'll be talking about the classical Hall, quantum Hall, fractional quantum Hall, and bit of anomalous Hall effect. Yeah, so each week we will build our understanding of these mesoscopic systems, and these are the fields which are like the cutting edge research where the cutting edge research is going on, and uh, so it's a cutting research area. I also work on this field. I'm an experimentalist, and I'll show my data also along with these. Whatever the theory I'll explain, I'll show my experimental data to demonstrate that whatever we see in the theory, how good it is producible, reproducible in the experimental part, counterparts, and will show you the quantum phenomenon of the resistance which we measure in our lab day to day. That's the characterizing tool for our. I work on the graphene system, and yeah, so there we do it. And in this course also, in this course, I'll be talking about graphene, which is a 2D material, and the whole part of it. Whole part of it. Yeah. So this will be an interesting journey, which will be the intersection of the quantum mechanics, material science, and what is the emerging technology, the being said the fundamentals of the resistance, which is derived from nowadays from the quantum Hall effect, because of the accuracy of the quantum Hall systems, and then we'll go on discussing the condensed matter and the spintronics out of it, how you can lift the spin degeneration can go on the spintronic side. So having said that, let's move on to the what I will call the assignment 0, where I will just explain what are the prerequisites for the system for this coursework and the basics of the coursework, starting the basic of the coursework, how the classical and all those parts. So the first question which I phrase here is Hall voltage and Hall effect. Question which I phrase here is Hall voltage and Hall effect. But what is Hall voltage and what is Hall effect? So with this one, I will start. So if you have a system, for example, you have a normal conductor. You have a normal conductor, you apply a bias, you apply a battery to it, voltage, and then let me call the 4 points. This is A point, this is B point, this is C point, and this is D point. Then there will be a resistance between, there will be a longitudinal resistance between RAB, will be finite, non-zero. Because of the scattering in the system, there will be some resistance in the system, and RAB will measure to be the finite, which will be equals to RCD. But in B equal to 0, this is whatever I'm saying is in B equal to 0. But in RAC will be equals to RPD will be 0. And this you can derive because these two potential will be equipotential surface A and C point if they are like right on the aligned part, and the B and D, and there the resistance will be 0. This is in the case of the zero magnetic field. But now if I ask you what will happen if I apply a perpendicular magnetic field, which will be perpendicular to the direction of the current, then in that case, things will change and there will be a potential difference between A and C, and which will give a finite resistance in the system in the transverse direction. And that is the Hall effect, which was first observed by uh, the scientist named Hall, and the full name was Edwin Halbert Hall, and he observed it in 1879. So, going on that, let me just example. Here I'll just phrase the paste. I'll just second. So just fill. Let me just copy it and paste it. It should paste it. Maybe there is some error. I will just draw it manually. I had a drawing of this circuit, so I'll just draw it manually. So, for example, you have this here circuit, which is like this. And in this one, you apply a voltage. You apply a battery here. And so the current will flow, right? And there is a thickness, certain thickness of it. So let me just draw the thickness part of it. So yeah, so say this is your length of your system, which I call L. This is width of your system, which your sample, which I call W, and this is the thickness, which I call the T. Now, since you have applied the voltage here, a bias basically, which will move the carriers in this X direction. So this, let me call this one as X, this one as Y, and this is the Z direction. Now the carrier will be moving. Since you applied this voltage, the positive side on this end, this electron will be moving like, so if I just keep it the way it is, so electron will be moving in this direction. Or if I change just the polarity of the battery, then I'll be consistent with my notations. So I'll just change the polarity of the battery. This will help me being inconsistent with the whatever the drawing I have. So I'll just go on putting this one here and this one here. So the current now, since they're electron, they will be flowing from this like this, electrons in zero magnetic field. But in presence of the magnetic field, if you have a magnetic field which is perpendicular like this B, which is in the plus Z direction, what will happen? So let me just call it. Consider a conductor of length L, width W, and thickness T. You apply a bias in the X direction V here, because that electron will move in this direction from positive X to the negative X direction. So current flowing in current is flowing in plus X direction. Remember, current and electron have their different opposite direction basically. So electron will flow in the negative X direction. So the force on the electron, because of this magnetic field, will make it curl. So it will start doing this. And in that case, if magnetic field is applied in plus B direction, magnetic field is applied in plus B direction. In that case, the force transverse force on the carriers of charge Q will be F is equals to Q. Here Q is minus E, will be Q V cross P. Here for us, the V is they are moving in the minus X. Since we are the current is in the direction of the plus direction, so we'll take it to the minus Q. V will take it to Vx cross Pz, and that will give us minus X cross Pz will be minus Q V P. So this will generate a, so this is the force which will be there on the carriers, which will move it towards the transverse direction. So the electron will go in the direction of, so if you just, instead of Q, you put the direction, the Vx for the electron is minus, right? Minus X. And here you put your charge carrier minus E. So that will give you minus Q minus EVB. So carriers will be drifting in minus Y direction. pi cap. So electrons will be accumulated on this side, this edge, which is minus y. Now they will be getting accumulated, but after a certain accumulation, there will be electric field because of these carriers. And the force because of this electric field will counter the force, this Lorentzian force, and which will give rise to the balance between these two. So force due to accumulated charges at equilibrium. So F, let me call it F1, and this is F2, will be E times minus E times E capital E, which is the AH. Let me call this whole electric field basically. And at equilibrium, F1 will be equals to F2, and that will give rise to EVP is equals to EH. So this essentially gives you V times B is equals to EH. So yeah, so and we know VH is the whole voltage will be electric field times W. This is the width. So here, okay, I missed a factor of B in this case, since this was just the force and B cross B. Yeah, yes, it's W. So this will give like VD times this one to be there. So now this EH, I write V, B, and W. And we know from drift velocity equation, V is nothing but I by N Q width and area. Basically I N Q A, right? I is equals to minus NEA VD. So this one, V will be this. And in that case, we will write VH is equals to minus I by N E WT multiplies by B times width of the sample. And this VH will be in this case minus I B by NET. Now this is the whole voltage which gets developed because of charge minus E. So the general expression can be written as minus, instead of IB by NQT, if the charge is Q. So you can see whole voltage because of charge Q. That was for electron. Now the whole coefficient can also be defined out of it. And RH is defined as VH times the thickness by IB. That will be equals to 1 by NE and Q. Basically, this is the whole coefficient. So what it does, in presence of the magnetic field, in the classical part, if you see your RH, there will be electrons accumulation on this end, and if because of that there will be a finite voltage which will get developed between these two ends, This we call the VH, and this is what we call the classical Hall effect. This is the classical Hall effect, whose equation is derived like this. For this work, so this was first discovered by Edwin Hall, and discovered by Edwin Hall, Edwin Herbert Hall in 1879. The material in which it was discovered is gold. And at that time, he was a graduate student at Johns Hopkins University, and he was the first to observe and explain the physical origin of this transverse voltage. So that's the whole. So that's about the Hall voltage. So in summary, if I have to write what is the Hall voltage, we say that okay, it is a transverse voltage which gets developed, which is developed across a current carrying conductor it can be a conductor or a semiconductor placed in a perpendicular magnetic field. And it arises due to the Lorentz force acting on the moving charges, which cause them to accumulate on one side of the material that we have discussed. And this value of VH, Hall voltage, is IB by NQT. This is what is the Hall voltage. Now, since from this equation you can say, let me call it equation 1. Since from equation 1, one can, by measuring VH, one can determine the polarity of the charge carriers. What I mean by polarity carriers, whether they are electrons or holes. So that can be determined from the measurement of the VH. For electrons, VH will be negative. For holes, VH will be positive. And this is very important and very useful in case of the graphene, where you have electron in the conduction band and hole in the valence band, and that helps you calibrate the capacitance of the devices also. So this is very important. So this is about the Hall effect, classical Hall effect. This is the classical Hall effect. Now, moving on to, let me just then rephrase the next question. So let me phrase it. So what are the application of Hall effect? Application of classical Hall. Because whenever you talk of some phenomena, if it's a fundamental phenomena, in future it gets translated into the industrial applications, and I will just discuss about one or two of them, that how it's being done. So since you see that VH is proportional to, is equals to basically IB by NQT. So application 1 is determining the amount of current in non-invasive circuits, where you don't want to cut or place something, but you want to measure the current through that wire. For example, if this is your current carrying wire, which is placed in this direction, so the current is moving like this. Now, if you, without cutting or doing anything on this wire, you want to measure the current of this wire, what you do is you place your whole sensor like here, right? And you measure the voltage, you pass current, little current between these 2 points, and you measure this voltage between A and B, VAB, which is nothing but V whole. Since current carrying wires acts as a magnetic field, they have their magnetic field. So the magnetic field here will be perpendicular to this sample. So a B is in the Z cap direction. You have AB, the similar problem we solved, and you can measure the VH, the current you are passing, the I, that you know. Q, you know what are the charges, it's, whether it's electron type or hole type. Carrier density, you know at what carrier density you are doing the measurement. Thickness of your sample, you know. You can easily estimate the B, which can be translated into, let me say this is IG, I1 be linked to I1 by B is equals to mu naught Ni by some factor, that is depends on the which medium you are in and those proportionality constant. And then, so the current can be measured in wire CD without invasive methods, without cutting it, without putting any contacts on top of it. You basically can measure the current through this wire CD just by putting it near the whole sensor near to this wire. This is one application. Another is you have seen the mobile phone, which we all use, right? The compass in mobile phone, which help us navigate through the GPS and all those things. Compass in mobile phones. So this also has the sensor, right? Your sensor will be there in which the circuit continuously supply the voltage A, and then these other points A and B. They measure the voltage between C and let me call this C and D. So VCD will be VH here, and that is again we can write IB by NQT. Since Earth has its own magnetic field, so this B will be determined by the Earth magnetic field, and knowing the direction of, knowing the voltage of B, the voltage of VH, one can determine magnetic field of Earth, and therefore direction north south. So this is how the compass works. Then they are also used in the accelerometers to measure speed. So what you have is like if your wheel is rotating, so for example this is your wheel which is rotating, what you do is you put a magnet here with north and south pole along with this whole sensor, and this will determine how much because each time a spike comes, these spikes comes near to this sensor, the voltage reading change, and it reads those changes and because in terms of the frequencies in a time series, and then it can translate it back to the speed. So that's another well known application of the Hall sensors. So with this one, this is the motivation why even the discovery which was made in the year 1879, it's so relevant nowadays. So let me just write somewhere. If I Let me just re-emphasize that it was in 1879 discovery and still used in our mobile phone, accelerometers, or being in the electronic circuits where you don't want the invasive methods to measure the current precisely. You use these kind of circuitry. Now moving on to the next one, next question, which is like solving a problem based on the formula which we derived. So it goes like a rectangular. Okay, I'll just copy paste it so that it becomes easy for us. I don't have to write it. Yeah. So this is the question, which says that a rectangular semiconductor bar length is given. Answer. So length is given. Length is 15 mm. Width is 6 mm. Thickness is 1.5 mm. Okay. They carries a current of I is also given, which is 25 milliamps. Good. Magnetic field B is also given, 0.2 Tesla. And they are asking VH is also given, 50 microvolt. They are asking calculate the Hall coefficient. We have calculated the Hall coefficient. RH is nothing but VH times T by B times I. Right? If you come here, so the RH V times VH times T by IB. Right? So let's just substitute the values. VH is 50 microvolt, 10 power minus 6. Thickness is 1.5 mm. Then your B magnetic field is 0.2 Tesla and your current is 25 into 10 power minus 3. So your RH, if you calculate it, it will be 50 into 1.5 divided by 0.2 into 25. So this will go like 5, 10, 5.3. So this will be 10 into 3 by 2 into 10 power minus 6. So this 3 by 2 is 1.5. So it will be 15 into 10 power minus 6. And it will be having a dimensions of 1 by NE, so Coulomb inverse, and meter square. Meter, yeah. Yeah, somewhere like this. So these will be the numbers for it. So this is how we approach the problem. So if the quantities are given, for example, in this case, length and width are of no use, but the quantity which are of the use for this problem are the thickness, current, magnetic field, and the VH. And that helps us solve the problem. So this kind of the problem comes in the exams also, and this will be the similar problems will be there in your assignments also. So I think you would have seen it also. So just to meter cube per coulomb, since it's a 3D material. Now, similar to it, inspired from it, we have another problem. Let me just write question number 4, which will be that if you have an n-type gallium arsenide wafer of thickness, the current, voltage, length, everything is given, then you expect, then what is the expected Hall voltage? Because it should also be based on the parameter, it can be computed, right? Because so this is the question. You have an N-type gallium arsenide wafer of thickness 0.8 mm. So let's just write what are the key parameters from if you are so approaching a problem, always write the key parameters that helps us solve the problem. So T is 0.8 mm, width is 8 mm, length is 50 mm. Magnetic field is also given, it's zero point 0.4 Tesla, and current given is 15 milliamperes. Hole coefficient is also given, RH is also given. Oh my god, everything is given. Minus 4.2 into 10 power minus 4 meter cubes. Yeah. So compute the expected hole voltage. VH they are asking. So we know from the above equation, if you see, VH will be related by B times I by T, then will be multiplied by RH. So let's do it. VH will be nothing but B is magnetic field is 0.4, I is 15 milliamps, RH is minus 4.2 into 10 power minus 4, and the thickness here is 0.8 into 10 power minus 3. So let's just compute it. So if you do the computation, 4 to the 8.1 and it will be 0.2. So point cancels, and then 2 you just divide minus 2.1. So 15 into 2.1 into 10 power minus 4. So if you do so, the answer which will come out of it will be roughly around, if you do 15 into 2.1, it will be 3.15, I think. Yeah, it will be 3.15. H will be 3.15 to 10 power minus 4. So if you have to compute expected voltage in, like, this is the voltage which will be there. Volt. Minus 3 volt. So VH you can write minus 3.15 millivolt. Yeah. So if this is clear, then let's move on to the next problem, which is that what will be the relation between the hole mobility and the hole coefficient. So if you see the question is what is, this will be question number 5, relation between hole mobility mu h to hole coefficient and electrical conductivity. Yeah. So what is the relation between the hole mobility to hole coefficient and electrical conductivity? We know the hole mobility sigma, for example, let me write sigma conductivity will be Ne mu h. Ne mu. This is equation 1, right? This is the standard one which we use, sigma equals to Ne mu h. And where sigma is the conductivity, N is carrier density. Uh, E is electronic charge and mu h is uh, hole mobility. At the same time, we know that RH, which we derived, was 1 by Ne minus 1 by Ne. Right? So RH was 1 by Ne. If you compute these two together, since you just, instead of this, sigma is equals to, you substitute the value of 1 by Ne, so it will be mu h by RH negative. Since negative mobility doesn't mean anything, this implies mu h will be RH times sigma and modulus of RH times sigma, where mu h is, this is Hall mobility, RH is Hall coefficient, and rho is, sigma is conductivity and rho is resistivity. So this is the relation between Hall mobility and Hall coefficient. Okay, if this is clear, then I'll move on to the next question, which is now the violation of what you call the classical Hall effect and the bringing of the quantum Hall effect. So I'll just question number 7. Definitely we'll be discussing the quantum Hall effect in detail in the next class, but here is a quick overview. So what is quantum Hall effect? Yeah. So it is a quantum mechanical phenomena observed in the two-dimensional materials at low temperature. Low temperature is needed, otherwise the classical counterpart will just obscure these because of the thermal broadening. And high magnetic field. High magnetic field is needed to split the energies. So they are well separated and they can be easily resolved. High magnetic fields. Unlike the classical effect, the Hall resistance. So the difference between the classical and the quantum, unlike the classical Hall effect, the Hall resistance in quantum Hall effect becomes quantized in discrete values. So your RH will be quantized in units of h by e squared times 1 by nu. So this h by e square is a constant which is equals to 25812 ohms resistance, 25 kilo ohm that we say, and this is known as, this constant has its name, which is on the name of von Klitzing constant. This name is based on the scientist name von Klitzing, who discovered this phenomenon of the quantum Hall effect first in the gallium arsenide system. And for this, he won the Nobel Prize in Physics of 1985. So here H is Planck constant. E is electronic charge. And nu is the filling factor. So if I just okay, let me just write it. Discovered by von Klitzing in I think 1979. Nobel Prize in 1985. And this is all about in gallium arsenide system. It was discovered in gallium arsenide system. Gas basically. It's a two deck. It's a two-dimensional system. Two deck electron gas. Two-dimensional electron gas. So uh, if you see the key difference here, your RH is H by E square by Ne. RH quantum Hall is H by E square times 1 by nu, where nu belongs to integers. Nu is integer. But classically, RH 1 by Ne minus 1 by Ne. This is discrete because nu will take either value 1, 2, 3, 4, but here it's continuous. It is a function of carrier density n. Here it's not a function of the, of course it's a function of carrier density, but in a different aspect that it will be discrete, but this is a continuous. And why it happens? That's something that's something fundamentally different for these two systems, classically and the quantum Hall. Classically, you explain it from the Lorentz forces, how the Lorentz force modulates the carriers to go on the transverse direction. But on the whole quantum Hall effect, you have to incorporate the quantum physics. Otherwise, it's not possible through the classical mechanics to explain this quantized phenomena, because we know in the quantum mechanics, the energy levels are discrete. And that's something you are seeing here. And these are the discrete energy levels, basically. You are probing different energy levels depending on the which filling factor you are sitting at. So this is essentially a quantum phenomenon, and that's why it's known as the quantum Hall effect. So how it happens is phenomenon behind it. So you have this two-dimensional electron gas. It's a two-deck. Again, it has to be a two-dimensional system. In 3D, you won't observe these quantum Hall because the Z levels will just smear, will give enough states in between, and those quantum Hall will not be formed. So you have your current like this, I, your magnetic field will be perpendicular. So let me just draw the B. And this is the direction, and then you will measure the between these 2 points, the VH. Yeah. So if this in classical part, or when the magnetic field is 0 at low temperature, we know the Fermi. If I ask you how to draw the energy versus density of state, so what you will say, okay, you will tell me that, okay, up to a certain energy, which is what we call at t equal to 0, this is what I'm talking about, t equal to 0. You will say that at t equal to 0, this will be the density of state profile, DOS, versus energy. Okay, let me just copy paste it again. Otherwise, I'll have to draw them again. Copy and then paste here only, then paste here. Yeah. So let me just denote. This is DOS, density of state, and this axis is energy. So if I ask you to plot the density of state and energy for a metal, you will say that okay, up to an energy level they will be filled, and after that they will be empty. And this energy level we all know, we call it Fermi level, EF. Right? Now this is for B equal to 0. What will happen if you don't have B equal to 0? B equals to finite. And this, in this direction, basically B non-zero. And this direction is increasing B. So whatever the density of state you have here, in presence of magnetic field, it will get divided. It will get just, they will get degenerate basically. The states in the presence of the magnetic field, they will be equally spaced also. Yeah. So this is how the Landau levels will be there. These Landau levels will be filled, the bottom one, which are below the Fermi level. So these will be filled, Landau levels. This will be nu equal to 0, nu equal to 1, 2, 3, 4. Nu equals to 1, 2, 3, 4. No, 0 it doesn't make sense because 0 is not a good quantum number here. Nu 2, nu 3, 4, 5. Yeah. And your Fermi level will be here. So below the Fermi level, your energies are filled. This spacing is h bar omega c. So you are filled with the four filling factors, your Rxy here, which you call Rxy will be quantized in h by e squared divided by 4. That will be there will be 4 channels basically. But if you increase the magnetic field, what will happen? The spacing will also increase. So if this is your Landau level, then half of this Landau level will be filled maybe. If I take the Fermi level to be this only, and this one will be filled. So here you will be having 1, 2, 3, and the fourth will be empty, 3 will be half empty kind of thing, Fermi level. So by increasing the magnetic field, you increase this h bar omega c. H bar omega c is not omega, you know, EB by m star. So you basically, by increasing the magnetic field, you increase the spacing between the Landau levels so that they becomes easily observable. And that a low temperature is needed so that these states, which you see here, these states, low temperature you need because otherwise they will be thermally broadened on top of each other and you won't be able to distinguish these states. They will be thermally smeared out. So you need low temperature so they become sharp. You can easily distinguish between these states. You need high magnetic field so that the spacing is enough, which is, and that spacing basically your h bar omega c. H bar omega c has to be less than kBt to observe the quantum Hall phenomenon. Otherwise, you won't be able to see the quantum Hall. So this is the quantum Hall, about the quantum Hall, and if you measure your basically the Rxy in the system, if you measure the Rxy as a function of the magnetic field, what you will get will be initially in the classical regime at low magnetic field because the Landau levels won't be there. Then you will start seeing some little bit of plateaus, then they'll develop better at higher magnetic fields. So at I is equals to 1, nu is equals to 1, it will be 25812. Here at I is equals to 2, this resistance value will be 25812 by 2. Here it will be by 3, this will be 3, this will be 2 nu. So this will be nu equal to 1, this will be nu equal to 3, this will be nu equal to 2, nu equal to 3, and then so on. So this is what basically the quantum hole is. So if you see this one here, in this range of the magnetic field, it's the value is constant Rxy. Here Rh is constant, h by e square times 1 by nu, 1 by 2 here in this case. But classical should go as, because your Vh should go like B by Ne, right? With the magnetic field, it should increase linearly. But here it doesn't. So that tells you that there is a subtle fundamental difference between the classical Hall effect and the quantum Hall effect, and that's because of this quantum discrete energy levels which you are having here. By when you apply large magnetic field, these discrete levels you create, and depending where your Fermi energy is lying, you essentially are tuning your basically the filling factor between the quantum hole and the classical hole. These formation of these states, they are known as the Landau levels, nu equal to 1 Landau level, second Landau level, third Landau levels. That's what the common analogy is. You call them the Landau levels basically. And by increasing the further the electromagnetic field, you allow the electrons to interact with each other, and that leads to this phenomena of fractional quantum hole that we'll be discussing in the mid of the coursework. So if I let me just briefly tabulate it, whatever I'm saying. So if I tabulate the difference between classical and quantum Hall effect, so I will write first the feature, what is different, then I will write the classical Hall effect, then I will write the quantum Hall effect. So here regime, first regime, in which kind of material it is observed. So any conductor at room temperature, it can be observed. Any conductor at room temperature. But for quantum Hall effect, you need 2D system. This we will see when we will derive the expression of these quantum Hall conductivities and the degenerate levels. You need the low temperature and you need high magnetic field. This I have explained why we need the low temperature to reduce the thermal burning and the high magnetic field to make the spacing large between these states. Now, other subtle key difference is hole resistance. At some point, I just wrote it. I think it should be P by N. This is Rxy. Let me call it Rxy. This is Rxy. This is also Rxy. This is also Rxy. Yeah. Hole resistance, which is the Rxy. Here, it Rxy is minus P by Ne. But here, your Rxy will be minus h by e squared times nu. So this is continuous, linear. Here, it will be plateau and quantized. That's another key difference between these two. Then, longitudinal resistance. Rxx here will be finite in presence of magnetic field. But here Rxx will be 0 at plateaus. I'll come to it. What does the zero resistance mean? Is it superconductor? Because zero resistance we call the superconductor, right? But here it's not the case. I'll come to it what the zero Rxx means. Then origin. This is classical Lorentz force. Here it is quantum. And the Landau level physics will be there. The Landau levels are those discrete energy levels in presence of magnetic field. Edge states will be there because these at the boundaries these Fermi levels and these basically these states will diverge at the edges of the sample and they will interact. These states will intersect at the Fermi energies, and those many edges will be formed in the system. This we will be discussing maybe in the next lecture or next to next lecture. This one was discovered by Edwin Hall, and this one was discovered by Klaus von Klitzing, and so discovered by Edwin Hall in 1879, and this was discovered by Klaus von Klitzing in 1980s, 1979, 1980, a Nobel Prize in 1985. The first Nobel of this quantum hole. After that, the Nobel of the fractional quantum hole came, and this year, this Wolf Prize, which is given in the fractional quantum hole to Moti Heblam, Jalendra Jain, and one more guy. Moti Heblam is a faculty at Weizmann Institute of Technology, and he has received this Wolf Prize this year for he, along with his two other mates, has received this Wolf Prize uh, in the field of this fractional quantum Hall effect. This is just for information, and now moving on to the next question, which I will be taking. Since I have the time, I will take one more question. So question will be, what is the significance of zero longitudinal resistivity and conductivity? Zero longitudinal resistivity and conductivity. Both longitudinal resistivity and conductivity are zero in quantum hole. And that's surprising, right? Because zero resistance you call superconductor, but zero conductivity you call insulator. Isn't it contradictory? And actually, this is not a particular surprise. It just has to do more with the words, and we can describe the phenomena with this underlying physics, and it has nothing to do with the quantum mechanics. This can be explained in the Drude model itself. So, for in Drude model, under tau scattering time going to infinity, where there is no scattering, in the situation the current will be flowing. In the situation, the current is flowing perpendicular basically to the applied electric field. So E dot J, that's what we call conductivity, right? Sigma equal to E dot J. Since the direction of the carriers moving carriers is in the transverse direction, to the applied electric field. And E dot J is nothing but the interpretation of the work done in accelerating charges. So this will be 0. And what does it mean? It means that we have a steady current flowing without doing any work. And correspondingly without any dissipation. In fact, sigma xx equals to 0 tells us that no current is flowing in the longitudinal direction like an insulator. And that's what it is. In the bulk is insulator. Indeed, the bulk is insulator for this quantum Hall effect. And this is the first observed experimental phenomenon of this topological insulator, where the bulk is insulator and the edges are the conducting. This is not the usual phenomena you see in the metals. Like an insulator. And rho xx is equal to 0 tells us that there is no dissipation of energy. This is like perfect conductor. So what you have is like, for example, this CT, if you have, its bulk will be insulator. Its edges will be conducting. So there will be one edge like this. There will be another edge like this. If this is capital mu left and this is mu right, chemical potential. So this edge will always be at mu right potential. This will be at mu left potential. And bulk will be insulator. And your Rxy will be directly proportional to mu L, mu R basically minus mu L, the change in the chemical potential between these two edges. And that's what it is. So whatever you measure Rxy is just the difference between the two chemical potential, these two ends, with some constant in the front. And this is what the quantum Hall effect is. Quantum Hall. And if you see it with the classical counterpart, it's very different. Your bulk is insulator. In the classical physics, your bulk is conductor. And if you want to understand this mathematically, how the sigma xx and the rho xx can go to 0 simultaneously, then remember sigma xx is nothing but rho xx by rho xx square plus rho xy square. And sigma xy will be rho xy by rho xx square plus rho xy square. Now, at plateau, your rho xx is 0 because there is no dissipation. This edge is acting like a perfect conductor, ballistic transport. So rho xx is 0 and there is no dissipation in the system. And your rho xy will be finite. This implies your sigma xx will be 0 and sigma xy will not be equal to 0. Right? Your sigma xy will be equals to 1 by rho xy, and that will be not equal to 0. That's the difference between this classical Hall effect and the quantum Hall effect conductivities and the resistivities. And they go the longitudinal one conductivity and the resistivity goes to zero simultaneously. And this tells us about the nature of this quantum Hall effect, that the bulk is insulator, edges are conducting, the edges are ballistic transport. Each ballistic channel has a resistance of h by e square. If there is only one ballistic channel, nu will be 1, resistance will be h by e square. If there are two ballistic channels, we know the resistance adds in parallel, like inverse of the resistance, basically. The conductance adds. And in that case, your conductance will be 2h by e square, or your resistance will be h by e half of h by e square. If there are parallel channels, for nu equal to 3, it will be 1 by 3 of h by e square. And like that, the resistivity goes in the system. The temp load. So just to recap the today's lecture, we discussed about the course, what will be there in this course. That will be discussing about the mesoscopic systems, then electronic transport in classical and quantum Hall effect, then classical, quantum, fractional, and anomalous Hall effect. We'll be discussing cutting research area in this field, work in this field, and in this course we'll be talking about the graphene 2D material and its whole component of it. Then we discussed what is the classical Hall voltage, how it arrives, the definition of it. Also we write what is the Hall voltage and how it is dependent on the magnetic field, current, carrier density N, charge Q, and the thickness T, and how this VH is related to your Hall coefficient RH. This also we discussed. Then we discussed what are the applications of the classical Hall effect. One being determining the current with non-invasive methods, compass in the mobile phones, and in general compass with the Hall sensors, accelerometers to measure the speed in the machineries. Then in the next question, we computed the Hall coefficients given the length, width, thickness of the sample, current passed in the sample, magnetic field applied, perpendicular, and the Hall voltage measured. Depending on that, we computed the Hall coefficient RH, which is VH times T divided by B magnetic field by current. Then the next question, we computed the expected Hall voltage similarly with the formula. Then we derived the relation between the Hall mobility and the Hall coefficient. This is mu h is Rs times sigma. Then we looked on what is the quantum Hall effect, how this phenomena is different from the classical counterpart. So we observed that we noted that Rxy here will be having plateaus at integer fillings of integer filling. Filling is like how many lambda levels you have filled, nu that we call, and nu will be integer, and h by e square is known as von Klitzing constant. It has a value of 25812 ohms. It was discovered by von Klitzing in 1979, Nobel Prize in 1985, and in gallium arsenide system. Then we discuss how the phenomena works of this quantum Hall effect. What are the requirements for this to observe the quantum Hall effect? Then we quantified the difference between the classical and the quantum Hall effect. You can see these two sections. This is for classical Hall effect, and the right one is for the quantum Hall effect. Then we understood the significance of the zero longitudinal resistivity and conductivity, how they are arriving in the system. And we understood that, okay, in the system, the bulk is insulator, edges are conducting, and the chemical potential plays a big role in the system. And this is about this class. If anyone has any doubt, question, or suggestions, and they can drop their comment or can speak in the mic. I'm here to answer your queries. So I'll just wait for 5 minutes, and after that we will make the class complete. So if you have any question, doubt, please ask in the comment section or can speak with the mic.
Okay, if there is no any more question, then I will mark the class end. We'll see you on the next Saturday, 6 p.m.